Hi, welcome back to Unit 6. This is topic 6.3. Here we're going to talk about angular momentum and angular impulse. Just like we've been doing in most of the videos here, we've been kind of taking these linear quantities and transforming them into angular quantities. So the magnitude of the angular momentum of a rigid system about a specific axis can be described by the equation. Sorry, I was on eraser. L equals I omega. So L is angular momentum. I, of course, is the rotational inertia, so the rotational equivalence of mass, and omega is the angular speed. So it still has that P equals mv kind of look to it. Now, if you have, since we're here in AP Physics C, we will write this as a cross product, which is going to be L equals R cross P, which if we kind of put in our string, right, we get R cross mv, but that just simply becomes mvr, right, sine theta. Okay, and this part right here is very important because if you have a linearly moving object moving into a rotating system, that would be your angular momentum for that linearly moving object. Now, just like we did with momentum, there is the impulse momentum theorem, right, or angular impulse. I'm just going to call it J sub ANG. It's going to be the integral of the torque dt. Okay, so the amount of impulse is the integral of the amount of torque exerted on an object for that time interval, right? That's if your torque varies. If it's constant, the angular impulse will just be tau delta t. Okay, again, this linear to rotational quantity piece. Okay, now, if we want, now we could talk about the, angular impulse momentum theorem. So delta L is equal to the integral from T0 to T1 of tau, it should be a tau, not a T, dt. Okay, again, this is if tau varies, right? Your torque varies, but if it's constant, right, delta L is equal to tau delta T. So again, like just all this, like everything we talked about way back in the momentum unit holds true here. Okay, and there is a rotational form of Newton's second law, all right? So the net torque is dl dt. So what does that mean? When we're looking at an angular momentum time graph, the slope of that graph will be the net torque on the object, right? So if I look at this graph, if I want to find what is the net torque on that object at 2 seconds, I'm just simply going to find the derivative of that function at 2 seconds. Now on the other side, if I'm given a torque time graph, the area, right, under the curve will be our angular impulse, which is also equal to our change in angular momentum. So again, like these parallels between linear and angular quantities just continues to run through these last 2 units. All right, so let's look at an example. So we have a particle moving, a particle of mass 2 kilograms is moving in the XY plane at a constant speed of 0.8 meters per second in the positive x direction along the line y equals 4m. As the particle travels from -3 meters, x equals -3 meters to x equals positive 3 meters, what is the magnitude of its angular momentum with respect to the origin? Okay, so we have a linearly moving object in a rotating system. So what that means is if I have an object, it's going to be up here at right, at y equals 4 meters. Okay, and it's going to be moving from -3 to 3, right? And so it's going to travel along this y equals 4 meters, okay? And so what we need to do is figure out, right, how far is it away from the origin, right, once it hits that point? Well, that's easy. That's just 4 meters, okay? And so we have all the information we need. We know that it's a 2 kilogram object traveling at 0.80 meters per second. And then when it's passing the origin, it's 4 meters away. Okay. And so you end up with 6.4 kilograms times meters squared per second. Okay. So this right here is the unit for angular momentum. All right. So in the next video, we're going to, just like we did when we talked about linear momentum, we're going to bring in conservation of momentum.